Hi, let's start with the basic assumptions, the textbook assumptions of the classical linear regression model. So CLR means classical linear regression model, and you learned OLS, ordinary least squares estimator, for the regression model. So in this chapter, I'm going to review them, and I will distinguish how these two CLR and OLS are different. Rigorously, they are different, but in most cases, they are used interchangeably, which is not exactly correct. So let me explain. So let me start with the assumptions. The classical linear regression model consists of these assumptions. Typically, the four assumptions are discussed. Often, some variations of them are considered, but basically, the implications are the same. So first assumption is the linearity. So it is an implicit assumption that y is generated by this linear function of x. So the x is linear, and also the error term is linear. So error term is additively separable, and everything is linear in x. So obvious. And second assumption is the exogeneity assumption, which means that x and epsilon are uncorrelated. You will see. So why do I say it is a correlation? I'm going to, maybe you will do this in a homework. So I will later you will understand this more clearly. But I will just keep it as covariance equals to 0. And assumption 3, by the way, so uncorrelated, so we call that exogeneity. So we say that the variable x is exogenous, which is defined by this condition. X is uncorrelated with epsilon, or independent of epsilon, or mean independent of epsilon. There are different forms of exogeneity assumptions, but basically the idea is that x and the error term are not related, or x does not affect epsilon, or x does not affect epsilon does not affect x. So that's the idea of exogeneity assumption. And the third assumption is the full rank or non-singularity assumption. The idea, so the statement is, mathematical statement is, formal statement is that expected value of x prime, x transpose is a full rank. Think about this. X is k by 1 vector. So x transpose is 1 by k. So x prime is k by k matrix. K by 1, 1 by k. So k by k matrix. So expected value of k by k matrix is another k by k matrix. So it is a matrix, non-random matrix, because expectation was taken. It is not random. It is just some kind of matrix. You can think it as a covariance matrix. It is a full rank. Full rank means it is invariable. So this is maybe the easiest way to understand this assumption. So what we need is x primes, the covariance matrix of x is invariable. Matrix is invariable. You know what is an inverse of matrix. And just mathematically, this statement is equivalent to say that a matrix has a full rank or a matrix is non-singular. They are the same, mathematically the same statements. But I don't know why the full rank or non-singularity assumptions are more commonly used. Anyhow, inverse, the existence of inverse is what we need. And assumption 4, the last assumption, is finite second moment. What we need is a finite second moment here. So the expected value of epsilon squared conditional on x is finite. That is what we need. But being finite means it is a certain number. So sigma squared is our notation. But what we need is finite. And so the reason why I call this finite second moment is because we have an implicit assumption. The implicit assumption is that the data are IID. We have IID data, so 1I means identical distribution. So that means the variance of epsilon squared, the variance of epsilon is the same across all observations, right? That means if the second moment is finite, it should be one common number. So it is finite, and by the implicit assumption, they are identical. So combining those two, you can write the expected value of epsilon squared as one constant, right? Finite and constant, finite and identical, so they are the same. As I said before, if this guy, if this second moment is different across I, different I may have different variances, then we call that situation as the heteroscedasticity case, and then that violates identical distribution assumption. So we do not consider that case for a while, and otherwise this assumption is a homoscedasticity assumption, and that's what I'm going to use based on the IID assumption. And also another assumption is that we observe x and y and epsilon is not observed. What we observe and what we don't observe should be specified, should be assumed. So, but it's obvious, so it is implicitly assumed, not stated in here. And finally, beta is non-random. It's unknown, it's fixed, it's a constant. Later, there is an econometric model called random coefficient model, in which beta is random. Then, like if you relax this assumption, it becomes another model. So it is not stated. It is not stated here, but also implicitly maintained almost everywhere. Anyhow, those are the assumptions you have for a classical linear regression model. And based on these assumptions, you learned you can estimate the unknown beta using this method. From the data, you can calculate an estimator beta hat, which is called the OLS estimator, and you learned nice properties of this OLS estimator. It is unbiased, it is efficient, best linear unbiased estimator. It's consistent, and its standard error is given by simple form, blah blah blah. So this is what you learned in Econometrics 1 and in the basic linear regression chapter. And let me mention some variations. First, you may assume that epsilon, the distribution of epsilon, is normal, which is actually stronger, much stronger than my assumption. So it is epsilon, the distribution of epsilon given x is normally distributed with mean zero variance sigma squared. This replaces the assumption 2 and assumption 4. And this assumption is more restrictive, stronger. So not only this implies the mean and variance, but at the same time, it implies the shape of the distribution is a bell curve, normal distribution. And this is a stronger assumption, but in this, if you have this assumption, then you can do a better job. You can do a better estimator, called the MLE estimator. Maximum likelihood estimator can be implemented, can be calculated based on the stronger assumption. And in the end, we learned the MLE estimator is equivalent to OLS estimator in this case, because the OLS is the linear regression model is a special case. They happen to be the same, but in general, there is a general mathematical results that MLE is the best. Maximum likelihood estimator is the best estimator in general. So when you have a stronger assumption, you can do better. And you may allow for heteroscedasticity or autocorrelation, which means it relaxes this assumption. So you may just assume that the variance of epsilon is a general matrix. So it violates the identical and independent distribution assumption. So epsilon may be correlated. Epsilon may have heterogeneous variances. So IID assumption is broken, but we know how to handle, because linear regression model is simple enough, special enough, so it is not that difficult to handle the violation of IID case. And the answer is GLS estimator, generalized least squares estimator. You can find this estimator in any textbook. But however, we are not going to study this case because violation of IID causes much bigger problem when you make some changes on the linear regression model. The linear regression model is really, really simple. So those kind of problems does not make much difference. However, like later, when you relax a little bit of assumptions or make the model a little more complicated, then those deviations cause problems. So I just mentioned here, and I'm not going to discuss those variations maybe later. Okay, so far I gave you a bigger picture, what you learned, what you had to know, what you need to know at this point. And some variations, how you can view variations of the linear regression model with respect to the assumptions, the standard assumptions. I have not discussed the details about the properties about the estimators of OLS or GLS or MLE. They are coming later. So next time I will go back to make them more general and more abstract. And you are going to see how we can understand those assumptions and those variations and those estimators from step back, like you can view more general forest of the model. Okay, see you in the next video.